All right, with that, I'm going to hand it off to Fraida, continuing the theme of spectrum challenges.
There you go. There we go. Hello, my name is Fraida Fund. I'm a fifth-year PhD student at the NYU Tannenbaum School of Engineering. It's okay if you haven't heard of the NYU Tannenbaum School of Engineering, because we've had a little bit of an identity crisis in the last few years. So we're actually the result of a merger between Polytechnic University and New York University. And over the last few years, we've become the NYU Tannenbaum School of Engineering, but we're still the same old Polytechnic University, which has a long tradition of wireless research. And you already know a little bit about what a spectrum challenge is. It's a competition to create a radio design that can communicate effectively in non-exclusive spectrum. And you've heard a little bit about a kind of more complicated spectrum challenge, this DARPA Grand Challenge. But actually, there have been spectrum challenges going on a smaller scale for years now. And this is one I participated in. It's a DARPA Spectrum Challenge from a few years ago. And the basic idea is that there were two teams, both teams operating one radio pair on the same frequency. They go head-to-head at the same time, and whoever gets more data through wins. This is the final event of the DARPA Spectrum Challenge, and there have been others over the years. There's the DARPA Spectrum Challenge in 2013, which I participated in. Testbed has run a couple of spectrum challenges. Virginia Tech has run some spectrum challenges for students, also one I participated in. And there are a few coming up, both the DARPA one we've heard about, a continuation of the Virginia Tech student competition, and a continuation of the Testbed Spectrum Challenge. So these last three are coming up, and I encourage you to participate because they're a lot of fun. Now, besides for these spectrum challenges, there have also been classroom spectrum challenges. So in addition to these spectrum challenges that I have participated in and spectrum challenges I have not participated in, there are spectrum challenges that I have taught or that I have helped to teach. And actually, the first one came out of the original DARPA Spectrum Challenge that I participated in as a competitor. My team did not do well at all. We made it to the final round, but then came last in the final round, so oh well. But it was very educational, certainly, for all the members of my team, and we learned a lot from doing it. And so I immediately started thinking about how we could share that experience with our students as educators. And so we developed this course based on that spectrum challenge. It was taught for the first time by my colleague, Professor Thanasis Karakis at the University of Thessaly in Greece. And he taught it in fall 2014. After that, I convinced my department to let me teach it. In fall 2015, we did it again at NYU, and Thanasis taught it again, and he's teaching it again this year. So I'm here today to tell you more about the spectrum challenge that we've run in the classroom, and to tell you how you can do it yourself in your own classroom if you're so inclined. So here's a brief summary of the 6 steps that went into the NYU Tandon Classroom Spectrum Challenge. The first step was to convince the department to let me try this crazy idea because they're not really in the habit of letting PhD students teach random classes they've just made up. What we had going for us is that in the typical electrical engineering curriculum, we don't really have a lot of existing coursework that ties together all these different parts of radio engineering, RF systems and signal processing and digital communications. And this was kind of a nice way to tie them all together that filled a hole in the curriculum. And the other nice thing is that the wireless curriculum doesn't necessarily have a lot of project work that students can use to help them get hired. So the department saw that this really kind of filled a need and were willing to let me give it a try. The second challenge was to convince students to let me teach them this and to subject themselves to this experimental class. Most of them had not heard much about software-defined radio before, but they all kind of had this vague idea that it would be something that if they did it, it would help them get a job. So they were pretty much willing to go along with it for that reason. Step 3 was to construct our challenge arena for purposes of running this competition and for students to work on. And it's constructed out of old stuff I had lying around the lab, which is why it's using hardware that was kind of out of date even then. We had 5 usurps, 2 of them designated as transmitters, 2 of them designated as receivers. And we had a fifth one that was monitoring the output of the transmitters. And we had a T connecting the output of the two transmitters to the inputs of that monitor so we could see what was going on. And here's what it looks like in actual hardware. In case you're wondering, that sign behind them says, please keep this table neat and clean. So didn't do that so well, but this is what it looked like. Step 4 was to teach the class, which was a lot of work, but also a lot of fun. We did it in 3 stages. The first stage was to develop a radio peer that would communicate effectively over a channel with no interference. And this involves a lot of knowledge of RF systems, of digital communications, of learning the basics of software-defined radio, how to interact with GNU radio, how to run their designs. Next, we worked on communicating over a channel with a known interferer. So for this part, I would give them a reference design that would interfere with their design. So another radio that would run at the same time as theirs. And its behavior was kind of predictable, and they learned some techniques for dealing with it, basics of spectrum sensing and frequency agility and things like that. Finally, at the end, they were challenged to develop a radio that could communicate over a channel with unpredictable interference that was unknown to them. So in a head-to-head challenge against their teammates' designs. And we went through several scrimmages before the final tournament because the first time we had any student's design go up against any other student's design, none of the students' designs got anything through. So it took a few rounds, but eventually we made it to the final tournament, which was hands down the most fun I've ever had standing in front of a classroom. I was the announcer. It was extremely suspenseful. There were a lot of tiebreakers and last-minute changes, and it was all a lot of fun and a really great way to wrap up the class. But that's not where it ends. A lot of the students were interested in SDR as a result of the class. Some of them entered this competition at Virginia Tech. You can see them here holding this big giant check that they won. Others went on to work in the industry. Some of my students got jobs in SDR that they told me about. So it continued from there. Now, after hearing that, you probably have a few questions. Even if you don't, I'm going to answer these questions anyways. The first question you might be wondering is, if I'm an educator, can I run this class even if I don't have a fancy challenge arena like you? I know it's no Coliseum, but not everyone has even that. You might be wondering what was most challenging to students. What are the biggest challenges for them? And how can we make it a more effective educational experience? And finally, suppose I've convinced you and you want to actually try it. How can you actually go about replicating my fun? So first of all, the challenge arena. And here, you'll indulge me a little bit. I'm not actually a SDR person. I'm a testbed person. I'm going to tell you all about testbeds. Once upon a time, before I was an engineer, there was basically this. If you were doing networks or wireless, you could have an in-house lab with your own stuff that you can play with. You could have an emulation setup or a simulation setup, and that's basically all there was. And then this happened. Some people started thinking about the possibility of putting together programmable, flexible components that could be used for all different kinds of research and different combinations. And as a result, now we have this. So in addition to the in-house computer lab, the emulation and the simulation, we have test beds that run, let's say, as an overlay on the internet. For example, Seattle is a test bed that runs on end-user devices. There are distributed test beds that are made up of parts all over the world, like Planet Lab. There are test beds with programmable networks, so there are test beds with software-defined radio devices, SDN devices. And then there are test beds that are kind of a collection of heterogeneous test beds, which are basically what we call federated test beds, where members of the test bed can use different test beds with different capabilities and glue them together to do a more complicated system. For example, if you're interested in some next generation cellular wireless systems, you could connect a software-defined radio test bed and a software-defined networking test bed and build an entire system out of it. So these are some of the test beds. They're all over the world. The major test bed federation in the United States is called Genie. So that's this NSF project to develop computer networking infrastructure for research. And there are some federated test beds that are part of it. And there are similar efforts all over the world. here's my little part of the testbed world. I mentioned I'm a testbed person. I started being a testbed person as an undergrad. This was my undergrad summer research project. I put together this testbed, which is now part of the Genie family. It includes a cellular base station that you can see up there on the roof of the library of our Brooklyn campus. And over in the next building, we have a whole bunch of computers, and they each have some kind of wireless capability, either a cellular network card that connects to that base station, or Wi-Fi, or software-defined radio. Now, if you're an educator who's considering teaching networking or wireless, you might have some desire to build your own lab, and there are some good reasons for that. The benefits of using a shared testbed are that there are a lot of resources and it's free to use, whereas if you build your own, you have fewer resources, it's expensive, you have to buy them. On the other hand, with a shared resource, you can't be assured that it will always be available. It's shared with other researchers and students, whereas if you have your own in-house lab, its availability is much more predictable. With a shared testbed, there's some friction associated with accounts, with access, with learning how to use it. Since these are multi-purpose facilities, they're not necessarily as directed towards one task, so you might need to learn a little more to get started. Whereas if you build your own in-house facility, it's a single-purpose facility, it's much more focused, and it might be easier to use. And finally, there's always a concern that it might not stick around very long, and you might invest a lot of time in a platform that's going to go away, which is a valid concern. Because a lot of testbeds are funded. This is a totally fictional graph that I drew by hand, not based on actual numbers, but it's roughly accurate. There are a lot of testbeds that have been funded, far fewer testbeds that are actually built, and among the testbeds that are actually built, very few that are actually currently available. And by available, I mean, let's say available to people outside the lab that built them. And there are good reasons for that. Building a testbed is exciting, maintaining it is not. Building a testbed is something you can publish, and running a testbed for a few years is not really something you can write a paper about. Building a testbed can be, a thesis topic for an undergrad or a master's student. Operating a testbed is something you kind of make your student do on the side as long as it doesn't interfere with their research. And most importantly, building a testbed gets a lot of funding, and operating a testbed gets none. If anyone is out there and gives out money, yeah, it's a problem. So in deciding to use testbeds for this class, we took into account that we had some testbeds available that had been operating for years. They have been serving hundreds of users for at least 4 or 5 years now. And also these all share common architecture and software so that we can learn how to use one and then learn how to use all. So the question that started off this whole tangent of testbeds was, can you run this even if you don't have your own fancy challenge arena? The answer is yes. Here are some of the usurps that you can access with a Genie account, which is especially easy to do if you're an academic or affiliated with a US university. There are 2 major wireless testbeds in Genie. There is a testbed at Orbit, which is the one that hosted that original DARPA Spectrum Challenge. And there's the one called YTest at NYU, which is the one I operate. At Orbit, there are a few different facilities. There is a grid, which at one point was a 20 by 20 grid of wireless devices and is now somewhat sparser than that. But it still has a bunch of usurp resources that you can see here. There are also a few sandboxes, which are meant for testing designs. So those are kind of less congested, easier to get access to, but only have 2 radios each. And then at YTest, the challenge arena that I constructed for my course is still up and available to the general public, and it looks like this. The next question I raised at the beginning is, what are the biggest challenges for students? And there are many of them. It was very challenging. The primary challenge for students is that learning how to develop a radio design for this kind of task combines a lot of different areas that they haven't combined before, and that a lot of them may be kind of weak in. We taught this as a class for beginning master's students or very senior undergrads. So they had some background in digital communications, but most of them were kind of fuzzy on the concept of IQ signals and what it all means. They might have learned signal processing, but not in the context of wireless. very few knew anything about RF systems or about SDR concepts. And we actually had to introduce the class by teaching kind of a modified lab curriculum based on this talk some of you might have heard yesterday on why doesn't my signal look like the textbook. So we had a series of lab assignments that were based on commonly asked questions on the GNU Radio or users mailing lists, in which students were presented with a common symptom that people might see that's the result of the RF architecture or hardware impairment. And they learned in the lab why it happens and how to avoid it if possible, or how to recognize it. So these were all things that were kind of a prerequisite before students could even start developing their designs. On the other hand, once we got past that, we found that students were able to do interesting things according to their level. So even if you don't know a lot, even the challenge of trying to communicate over a channel with no interference can be a very useful exercise. We actually had high school students running it. Before I tried it on my graduate students, I used a couple of high school summer research students as my guinea pigs, and they did a great job, had a great design. And we've tried it out on some undergrads and some master's students, and even though they come in at different levels and with different levels of knowledge, they're all able to get something out of it, which was very encouraging. The other major challenge was not a technical or curriculum challenge, but it was a challenge that most of these students had never really worked on a big, complex project before. Most of them had never written any software that was more than a couple hundred lines of code, especially in the EE department. So most of them had never previously worked with a large existing code base or a big, complicated software framework like GNU Radio. Most of them had not previously used Git or other modern software development workflows. They had not all worked in teams before, even though many of them were master's students who come from, let's say, other countries where teamwork is not as common in the curriculum. And so that was a very big challenge for a lot of them, how to work effectively in a team and communicate in a team. And project management was very challenging, and that's especially true when you're working on a shared resource like a testbed. So testbeds kind of have a reservation system. Like here's what the reservation system looks like on YTest. There's a calendar. If you want to use a testbed, it's a time-shared resource. So you go ahead in advance and you click on the hour that you would like to use. And then there's a let's say, confirmation process. So multiple people can request the same time slot, and it's assigned based on priority. So if you've had many previous confirmed hours on the testbed, you have a lower priority compared to users who have not used it at all. And of course, when students start working on this, their first inclination is to go reserve days and days of testbed time and not use them, and then come up to the deadline and not win any of these conflicts, and then have no testbed time. That was something they all had to overcome. And this is another completely fictional plot that I made up, but it's also pretty accurate, which is that as you get closer and closer to the deadline, students start to reserve a little more time on the testbed, and then suddenly in the last week, there are tons of requests for testbed time, but there's only 24 hours in a day. So project management was a very big challenge, but fortunately, having had multiple challenges leading up to the final one, students had a chance to get used to the idea that it's a shared resource. You can't do it at the last minute. If you don't test your design, it's not going to perform well at all. And so they learned to plan in advance and be a little more organized, which was good. We did learn a few things about how to use competition more effectively, which was something we were a little concerned about, because competition can create a lot of anxiety, which is not necessarily productive in a classroom. So we've learned that healthy competition involves kind of a low stakes thing where the point of the competition is the fun and the learning and not what you get out of it. So it was very important not to tie the outcome of the competition to grades or anything like that. Instead, we tried to assign a high value to the quality of the work and the process of doing it, and not necessarily how highly they ranked in the final tournament. And to value all different contributions. So if someone had a particularly clever design that didn't necessarily do well in the tournament, still valued. So here are some specific examples of how we did that. So during our final tournament, we had every student give a team presentation about their design. And then during the tournament, we had an announcer. In this case, this is a tournament at the University of Thessaly a couple of years ago. And the announcer was emphasizing the radio behavior and ideas to highlight that. It was very important for us to recognize that the best designs might not do well in competition. So here's an example from my class. You could see here in the middle, there's this blue team that's just basically doing nothing, kind of transmitting straight down the middle. And then there's this red team that's doing a little bit of spectrum sensing and hopping around. And of course, the blue team, which is doing nothing novel at all, is going to get a lot more data through and is going to win the match hands down. So it was very important for us to realize going in that the best designs are not necessarily going to do well in competition, and it's especially important to value the learning and the process and not just the outcome of the match. And this was actually a very common theme that some of the best designs were likely to be the first eliminated. Okay. We also had a poster session following the final tournament where students had a chance to show off their designs and their ideas to other students in the class and also to other faculty in the department who could be invited to come. And of course, they also gave these presentations in the middle of the actual tournament in between their tournament matches. We made sure they were competing for bragging rights and not grades. So grade in the class was not in any way tied to their placing in the tournament. And we gave multiple awards, not just an award to the winner. The winners won a bunch of digital TV dongles to take home. But everybody won some kind of award, either innovative idea or best use of a particular concept. We made sure to value every kind of contribution because, as I said, the winner of the tournament is not necessarily the best design. Finally, you might be wondering how you can do this yourself. And for this, I would actually like to show you with the live demo, which hopefully will work. Okay. So there are a few steps here. The first step is to create an account on Genie, which, if you're a US academic, is extremely easy. You go to portal.genie.net. You click on Use Genie. I'm going to log out so I can show you creating an account. Okay, here we go. And when you choose to use Genie, you can start typing the name of your university in here. And so, for example, I can type University of Colorado at Boulder, and if I was a Boulder student, I can click on that and then log in with my university credentials. I'm an NYU student, so I'll log in with my NYU credentials. And it didn't ask me for login because I'm already logged into my NYU account, but if I hadn't been, it would have asked me. Okay. So the next step after creating an account is to set up keys because you access all the testbed resources remotely over the internet using SSH and using SSH with key-based login. So all you have to do is, in the Genie portal, open your profile and upload some keys to this page. Very easy. The next step involves actually joining a project. So in order to use a testbed like Genie, you need to either be a reliable, trustworthy person or have supervision of a reliable, trustworthy person because testbed operators don't trust students for some reason. So generally, you have to be either a faculty member at a US university or an equivalent. But in case anybody here wants to try out this experiment, I'm willing to be a reliable, trustworthy person to supervise anyone in this room, at least for this week. And so if you'd like to try this out, in the Genie portal, you can choose to join a project. Okay. You can look for the project called GRCon16 and click Join, and that will send a request to join the project to me, and I will approve it. And once I approve it, you'll have access to Genie at least until this project expires this week. The next step is to reserve time on the testbed. So I'll show you how that works. I'm going to log into the testbed with Genie. and make a reservation. And that's literally as easy as clicking on a calendar. So I'm going to pick some hour to reserve, and now you can see I have a request for this time tomorrow. Now, since test beds are shared resources, different people might be doing different things on them. And so when it's your turn, you need to start with a clean slate by loading a disk image onto all the hosts in the test bed. And we have a disk image that's provided for you that has GNU Radio and all the other stuff pre-installed. So the next thing I'll do is choose the disk image I want to use, which is called the SDR match disk image, and choose the nodes I would like to run it on, and just submit that. Now, this is all for tomorrow, but I already have a reservation today, so I'll run a quick match for you just to show you how it works. So I have a current reservation. I'm going to log into the test bed. Okay. In one of my terminals, I'm logging into the monitor node, and that one's going to run a shiny SDR web interface so I can see what's going on. Okay. And in my other terminal, I'm going to run the match script. And that's basically a script to which I supply the URLs and branch names of 2 GitHub repositories. And it's going to run my radio code from in that repository. So I'm going to start that now. And while that's running, I can visit the web interface in my browser and unpause it and see what's going on. So what I'm actually running now are 2 very simple designs. One that's just a radio that transmits straight down the middle, and another one that's like an on-off wideband. So you can switch between the ones you want to see. And that will run for, I think, 45 seconds. And at the end of that, it's going to tell me how many packets each of them delivered. And so it's literally as easy as that. If you want to get your students started, they can literally be up and running in 10 minutes or less. Now I believe I'm basically out of time, but I just want to point out that there's this link in my slides, which I assume are online. So if you want to follow these instructions yourself, you can go to this link and follow those instructions. Now I will take questions for, I guess, a minute, if there are any. And I'd also like to point out that Martin Braun has organized a little meeting of GNU Radio educators right now just outside if anybody wants to come.
So for anyone who wants to click on that link, remember the slides are all, for all the talks are being posted on the website. So you can go there, pull up her slides, and go to the link. So are there any questions for Fraida?
No questions.
So I'm just curious with the Spectrum Challenge and then hearing about DARPA's Spectrum Challenge. Have you considered modifying the rules so that it's a do no damage packets throughput winner?
Well, if Edis Research will send me a few more usurps so that I can make a test bed that supports that, I definitely would.
All right. Do we have any other questions? Can somebody? Thank you, Michael.
I know you mentioned earlier that you kind of tried this out on some high school students early on. I was wondering if you had any insight or thoughts on augmenting or paring down or bridging this kind of curriculum to target high school students with less fundamental math background or something like that.
Well, to be perfectly honest, I get high school summer research students every summer. It's part of a program organized by the K-12 Outreach Center in my university. And as you could expect of the type of students that participate in these programs, they're all highly motivated and very intelligent and very capable. They're not your typical high school students. Having said that, the ones I used as guinea pigs did very well. Even though they had no previous background in wireless, they were able to learn enough to actually do something meaningful. So I think it was, kind of a fun project to do in the scope of a couple months in the summer.
Thank you.
Any other questions? Nope. Okay, let's thank our speaker. Thank you, Fraida.